Hey everyone, welcome back to Chem Story. Today, we're talking about how to synthesize alkyl halides, not just as reaction intermediates, but as key building blocks in organic chemistry. There are a few different ways to make them, and the best method really depends on what you're starting with and the conditions you use. Some of the most common methods include radical halogenation of alkanes, electrophilic addition to alkenes and alkynes, and substitution reactions of alcohols. Let's break down each method and see how they work step by step. Let's start with one of the simplest methods, alkane halogenation. This reaction uses a radical mechanism where alkanes react with halogens like chlorine or bromine under heat or UV light. Now, since it's a radical process, selectivity becomes a big deal. Chlorination isn't very selective. It'll replace hydrogens at multiple positions. But bromination is more selective. It prefers the most substituted carbon, so the product is easier to predict. One thing to watch out for is overhalogenation. If you use too much halogen, you might end up with multiple substitutions and unwanted byproducts. That's why it's important to control how much halogen you add, so you get the product you want without going overboard. Next up, let's look at alkenes. One common way to turn an alkene into an alkyl halide is by adding HX. In this reaction, the hydrogen goes to the less substituted carbon, and the halide adds to the more substituted one. That's Markovnikov's rule. But there's a twist. If peroxides are present, the reaction switches to a radical mechanism. Now it follows anti-Markovnikov's rule. The halide goes to the less substituted carbon. This only works with HBr, though. Other hydrogen halides like HCl or HI don't follow the radical pathway as easily. There's another important reaction with alkenes, halogenation using X2. When alkenes react with chlorine or bromine, they form a three-membered halonium ion as an intermediate. This leads to anti-addition, meaning the two halogens add on opposite sides of the double bond. The final product is a vicinal dihalide, where the halogens end up on neighboring carbons. Since the mechanism goes through that cyclic intermediate, the reaction is highly stereospecific and always gives anti-addition. Now let's talk about allylic halogenation. In this case, we're not adding the halogen to the double bond itself. We're targeting the position right next to it. This reaction uses NBS, or N-bromosuccinimide, with light to generate radicals. That allows bromine to selectively replace a hydrogen at the allylic position without touching the double bond. Because the allylic radical is stabilized by resonance, the bromine can end up in different positions, depending on where the radical spreads. So you often get a mixture of allylic isomers as products. Just like alkenes, alkynes can also react with HX or X2, but the outcome's a bit different. When you add one equivalent of HX to an alkyne, the reaction follows Markovnikov's rule. The halogen adds to the more substituted carbon, giving you a vinyl halide. If you keep adding HX, the second halogen goes to the same carbon, forming a geminal dihalide. This works under both regular electrophilic conditions and radical conditions. And just like with alkenes, if peroxides are present, the mechanism shifts. Now it follows anti-Markovnikov's rule. The halogen goes to the less substituted carbon. But no matter which path it takes, adding excess HX leads to the same result, a geminal dihalide. Alkynes also react with halogens like chlorine or bromine. If you add just one equivalent of X2, you get a vicinal dihalide with halogens on neighboring carbons. But if you keep adding more X2, the reaction keeps going. The triple bond gets fully saturated, and you end up with a tetrahaloalkane. Unlike alkenes, where halogenation gives strictly anti-addition, alkenes go step by step, first forming a dihalide, then a fully halogenated product. Another key method for making alkyl halides is from alcohols. When alcohols react with hydrogen halides, the mechanism depends on the structure of the alcohol. Primary alcohols usually follow the SN2 pathway, a one-step backside attack where the halide kicks out the hydroxyl group. Secondary and tertiary alcohols go through SN1, forming a carbocation ion intermediate. And since carbocation ions can rearrange to become more stable, the halide might end up on a different carbon than you expect. So depending on the alcohol, you might get a rearranged product. If you want to avoid carbocation rearrangements, there's a better option. Instead of using HX, you can react alcohols with thionyl chloride, SOCl2, or phosphorus tribromide PBr3. These reagents follow the SN2 mechanism, so they're great for primary and secondary alcohols. And since there's no carbocation ion involved, you get a cleaner reaction with no rearrangement. Because SOCl2 and PBr3 generate strong acids like HCl or HBr as byproducts, pyridine is often added to neutralize the acid and keep the reaction smooth. And that wraps up the main ways to make alkyl halides from alkanes, alkenes, alkynes, and alcohols. Each method has its strengths, depending on your starting material and what you're trying to make. Now that you've seen the big picture, you'll be able to choose the right approach for the job. Thanks for hanging out today, and I'll see you in the next one.